an education blueprint for the AI age. We're about 2 minutes to start, so we're just checking that everybody's happy and can see the screen clearly. You have a chat option here. If anybody's got any issue with the sound or the technology at the moment, please enter it in the chat now and we'll see what we can do to fix, but we'll start literally in a couple of minutes. Okay, it's now 4 o'clock. Thank you again, everyone, for joining this session. It's the second session that we've had on Conrad's new book, The Math Fix, an Education Blueprint for the AI Age, which, as many of you will know, is a groundbreaking new book that exposes why maths education is in crisis worldwide and how the only fix is a fundamentally new mainstream subject. It's a book that argues that today's maths education isn't working to elevate society in a modern computation age, and instead students have been subjugated to compete with what computers do best, and they lose. So before I introduce Conrad himself, who's going to, in this session, answer some of the questions that I know many of you have, we're going to conduct a couple of quick polls, if that's okay. Wolfram is obviously very keen on utilizing data, so we've got 2 quick questions here for you to answer. First of all, we'd just quickly like to understand if you've already read the Maths Fix, and secondly, I can see you're already answering, have you joined the virtual book launch on 10th of June? Were you at the first session? And so this is your second session. So if we'll give you a few seconds just to have a go at the poll, and the percentages are going up nicely. Thank you very much indeed. And then as soon as you've all had a chance to answer, I'll introduce Conrad and we'll start the session. Okay, thank you very much indeed. That's a really great response. So as many of you, as I can see, many of you did join the first event, and so you'll know a little bit about the book, and many of you have read the book as well, which is great. You'll know that Conrad is co-founder and chief executive of Wolfram Research Europe. And over the past 30 years, Conrad's been a key part of the technology transformation that has brought maths, computation, and data science to the forefront of today's world. Conrad, as many of you know, will regularly appears in the media, talking about subjects ranging from the future of computation, artificial intelligence, and 21st century education. So what we're going to do today, the session's really split into 2 parts. From the first part, we had many questions from the first session on the 10th of June. We couldn't possibly ask Conrad all of those in a short session, so we've tried to group them into some key subject areas, and I'm going to pose some of those questions to Conrad over the next 20 minutes. And whilst that's going on, you have the opportunity live to use the Q&A, not the chat, the Q&A section of the site to put your own questions in today. And after about 20 minutes, we'll swap from the questions from the first session to pick out some of the ones that you asked today. So please get asking your questions and we'll sort those as quickly as we can. So Conrad, if you're ready to go.
I'm getting there. There we go.
Okay, so as I mentioned, we had a lot of questions from the first session, and they were grouped into a number of areas. And one of the first areas I think people were interested in touching on was an issue that you could describe really as the publisher challenge. So in many parts of the world, particularly in the US, it's often the major textbook authors and publishers whose ideas and content influence and change the curriculum. what can be done by all of us who are interested in your ideas to get the publishers to embrace the changes that you suggest? How can we help?
So when you say publishers, you're meaning the people who are, putting forward, in a sense, the curricula to everyone in schools, and that's how we mean publishers? Is that right?
Yes, it's some names were particularly mentioned. People like Pearson, who have a hand both in the creation of the textbooks, but also often in the assessments and examinations, and they often drive what is happening with the changing curricula.
So I think the question you've really got to zoom out to is, what is the linchpin of kind of making a change like this? And the linchpin is sort of somewhere around assessments and the books and how we get teachers to teach a particular curriculum. In the end, the publishers need to see a market for what they're trying to publish. And so they need to know that students want to learn this. They need to know that, it's a good qualification, so the students feel like they can get to college. And all of those things sort of need to come together. So I think one way to do this, to help, it's a kind of an ecosystem that needs unlocking. It's got jammed. There's a log jam, and we're trying to unlock it. And the question is, which bit to unlock? And you're asking specifically about the publishing end of it. I think one way is just to show them what's possible. And we've started to do this with our computer-based maths modules, and to try and explain that to them. And another one is to give a sort of example of what one can do. Run courses, show a different way to achieve things. And to start to get people on the ground actually using these things as an exemplar, to show that the system change might make things so much better. I mean, I think that's the sort of way you can start from the publisher angle. And one thing I discuss a lot in the book is not only that, of course, the main focus we have is change the curriculum. It's the subject, and I used to have a chapter which I actually took out of the book called, or at least I took the heading out, called "It's the Subject, Stupid." A little bit like, I suppose in the Clinton campaign in the US, it's the economy stupid at some point. It's the subject stupid. In the end, it's the subject that's critical to what we're doing here. But the delivery of the subject has to change quite a bit to allow this subject to change. And often some of the current publishers and things can't see how to make that delivery change. And it's a mixture of technology and how one might think about the change in pedagogy, which is required. And of course, at the center of this, what is the subject we're really delivering?
Okay, thanks for that. There were a number of questions around that theme. But I think it'd be quite interesting to move on to a separate topic, which is, I think, really summarizes practical ideas. So I had a number of people ask the question that as parents of young children, how do we take advantage of the ideas that you put in the book, Conrad? To what extent do you feel the book can give support to practical ways and ideas on how to teach people's own families, their own sons and daughters better maths?
Yeah.
And I guess as a corollary to that, there were a set of questions from people who were interested in how they could use Wolfram notebooks alongside and aligned to the book.
Okay.
And was there any plan to release anything that enabled that to work better?
So look, let me take this on two levels. I think the level in the end that we want to achieve, the big sea change over the coming years, is a fundamental shift in the subject to be a computer-based math, computational thinking, much higher level, more conceptual subject. That's where we want to be. But that requires big system change. And I think this question is, what can we do now? We can't change all the government's policy makers. We can't, not change them, but change what's happening at that level instantly. That's a long period. I think what we can do now is several things. I think firstly, we need to think at primary level onwards, start from the actual problem that might be of interest to solve. But in the end, what is mathematics? It's one of the world's greatest problem-solving systems. So let's take problems that might be of interest to that age range of child, of son or daughter, let's use every opportunity to think computationally, to take examples, to say, is this cause? I wonder if this causes this, or it's just correlated. I wonder if what that means. Does eating more chocolate cause more Nobel Prizes? Or are they somehow correlated? Because countries that eat lots of chocolate might be a little wealthier, and they might be able to fund research better, or those sorts of questions that seem interesting. That's one sort of thing we can, I think, way in which we can start to imbue kind of interest in using the power of mathematics to solve problems, rather than let's take some very abstract mathematics which you have no idea how it's connected to your life, and one day, hopefully in the future, you'll connect it up, by which time most of our sons and daughters have been lost somewhere in the ether. And it's kind of like they thought maths was boring and tedious and they wanted to give it up as quickly as possible. So that's one way. I think another way is this, that people get lost easily when they start doing mathematics, and particularly, I think, slightly later in primary, when they start getting more abstract, solving equations. They don't know why they're doing it, get lost. One aspect of that is understanding that maths, in a sense, is a process you apply. And we talk a lot in the book about it's a 4-step process. Define the question, abstract it to maths, take that abstract question, compute the answer, magic step 3, and you get an abstract answer. And then step 4 is where you take the abstract answer and go back to answer the real world question. That process, for reasons I find difficult to understand in much of education, we don't use that process before it's really needed. And even then, many people don't really think explicitly about it. When you have very simple problems for, let's say, and I give this example in the book, a child, how many sweets? I've got, 12 sweets. I've got 4 friends. How can I divide them fairly between my friends? Now, obviously, that's a division sum. But you can use define, abstract. You can use these 4 steps at that stage before it's critical. And you want to get very used to this rhythm of using this process. Okay, I'm going to define the problem. What does fairly mean, by the way? I mean, are all my friends equally deserving? Is it reasonable to divide these equally? Does it fairly mean equally in this case? So that's an interesting question in its own right. If I had 11 sweets, not 12, and I'm dividing between four students, can I break sweets? Or I should say, by the way, for the US audience, sweets equals candy, and so forth. So you can step through these, and that in itself gives confidence, and the confidence, I think, enables one to use this process to solve things when one gets further up without getting lost. And by the way, one of the things we've done is to produce a poster of our helix, which I think is, the idea that you can download that freely and just put it on your wall and point to which step you're at in the process, which I think, again, helps to reinforce this. So I hope that's a couple of ideas that we can use instantly, even if we can't change the whole system to start with.
Okay, thanks for that, Conrad. There were a set of, I guess, related questions in a way, based on a comment that you made in the first session, that there still was a price for hand calculating in early elementary grades. And so a number of people, I guess, have asked for something that I suspect isn't easy to say, but where does the transition and how does the transition happen? What's your view on that?
So look, I think what I'm saying about use the best tools for the job, use this as a tool, start from real problems, all of that applies all the way through from age dot to age 100 plus, right? There's no difference in that theory. The question is what's going wrong at the moment versus what we know. There are a lot of things you learn in very early primary, like we just talked about division or multiplication or adding, where you do still use those every day, but you don't use them on complicated numbers. You do estimates in your head with times tables. You certainly understand the idea of division. We just talked about dividing candy or sweets between different of your friends. But that problem is, there are 2 bits of the problem. There's setting up the problem. You absolutely need to understand what the idea of division is. Then there's actually doing the calculation, 12 divided by 4. And those are useful things to do. It's good to know that's 3. It's useful. I could type it into my phone or whatever, but actually, being able to do that quickly is just very helpful. So I think one criteria, I think what you need to think about is what are the criteria for when you do learn stuff by hand, versus learn particularly the calculation element of this, the step 3 by hand, versus when you just decide you're going to use a computer. And I think criterion 1 is, in the real world today, people actually use this still. Okay, so that's criterion 1. And I use times tables in my head just to estimate things. I could use a computer. That's fine. It's not a most pinnacle of anything, but of any primary education, but it's kind of useful. So that's 1. The second criterion, I think, is that learning it by hand somehow gives you an understanding and a power to go further that you miss out if you don't learn by hand. You miss out on if you don't learn that particular thing by hand. I think you've got to be really, really careful of this. So I think there are a lot of claims made for things you need to learn in the real world, for the real world, that really are not stepping stones to that and actually aren't necessary. But there are a few cases where I think it is useful to see a simple example by hand or to play with it yourself. The difficulty you've got here in this criterion is distinguishing those. And I know when we've been building computer-based maths materials, it's been incredibly difficult for us to figure out, you know, in a sense, what was really essential to now in us understanding this problem, and what do we want to just put into the materials because we all learnt it that way, because of course we've all learnt maths traditionally. So it's kind of like anybody who has much to say about this right now has learned a certain amount of maths traditionally. We've learned all these steps to get there. What is it you needed in that edifice to be able to understand where you go forward to? So those are 2 criteria I use. And I think what you find in most educational systems at the moment is the early primary is pretty sensible. We need to know many of the things in there. I think it could be supplemented with some things like machine learning, which actually I think we introduced very early. I think there are perhaps some new modern ways in which we can do the pedagogy, which is better, but I think overall not bad. Then you go up to maybe, it depends on the jurisdiction, age 7, age 8, age 9, something like that, and it starts to really diverge. You start to get solving equations in ways that seem completely abstract. And by the way, that's when we see a lot of people fall out and get frightened by mathematics. That's the real turn-off time. So I think that's where things seem to be going wrong and where we really need to make a change urgently.
Okay, that's probably a good point at which to leap off into how the change could be made, Conrad. There were certainly a lot of teachers on the early session who were keen on the call to action and were particularly keen to say, yeah, we'd like to overhaul or transform the mathematics curriculum. But what are the 2 or 3 things that we could really do to contribute to the journey over, say, the next year or 2? Because in the end, it's teachers that have got to help make this happen.
Okay. I mean, I think some of the things I answered earlier on about, you know, in a sense, how to work with your students, you know, whether it's the process or whether it's starting from real life problems. I think those are, you know, key things for teachers to do. Hang the poster on your wall, help to work through, even with traditional problems. It doesn't matter, even if you've got to do the calculating by hand. Let's be clear when we're solving our quadratic, when we're defining it, when we're abstracting it. If there is a problem, we define. When we are moving from that to calculating and to interpreting. I think the other thing we should try to do, if there's space, is throw hard problems at students, messy problems. You know, the world is full of extremely messy problems. Most of the problems in the world are very, very messy. And stop stripping out all the, you know, all the interesting gunk from the problems. And the more there's space to do this, to go off-piste a bit and to try problems that somehow involve, you know, we were talking about quadratic equations. They might involve equations, but they might be much harder equations. And the equation is wrapped in the middle of kind of the, in a sense, the, you know, the problem you're trying to solve. And at least spend some time doing that. Because I think when you then come back to the routine work that you have to do for the assessments, it may be more in context, and it may actually help the students, even if you weren't practicing the calculating skills that they need to do. So those are a few things. I mean, I think in sort of more, I mean, because there's several parts to this, I think. One is what we can do on the ground practically with our students today. Another part of this is what can we do to push the authorities and also to give them space. And so I think it's really important as parents in particular, and as teachers and as industry leaders, to be able to go and really, you know, in a sense, with one voice, explain we need change because we're not equipping our students for what they need in the future, and to continue to have that in the back of one's mind. I think also if you're a teacher, not of mathematics, but of, let's say, science, there are many places you can throw in sort of computational thinking to some of the science curricula, and it will fit with them. Let's say you're teaching biology. I think in biology, there's lots of space to make things more computational, and that will support the existing curricula. And so that's another way in which I think we can really help to push this agenda.
Okay, thank you for that. There's a related set of questions about scaffolding the direction of change. So if one gets to the point where policymakers say, yes, this is the direction we want to go, what's the sort of scaffolding that can and should be provided to help those teachers who've then committed to go on that journey? How do you get them into that problem-solving position? Sometimes it puts them out of a comfort zone. How can you help keep them on that track?
Look, I think for teachers, this seems very scary to start with, right? I mean, you know, we're asking teachers to basically take a subject they didn't learn themselves exactly, because this is a kind of a new subject in many respects, to go off and it's a scary, I mean, maths is always a scary subject in some sense, because, you know, it's easy to show that you're, in traditional maths, you know, it's easy to see you're right or wrong. It's easy to get caught out in a way it probably is harder in history or teaching English or something. And so that means that you have to have good confidence. And I think one of the key words for teachers in all this is how we help teachers get more confidence. And by the way, both in the existing subject and in the subject I'm proposing. Look, I think there are a number of ways. Obviously, there are familiarity that is helpful with this. I think something that we've seen a lot, which is encouraging, is one of the problems with traditional maths at the moment is it's awfully abstract. And if you really pin many teachers down and ask them, so exactly why are you teaching this topic to these students in terms of their life? I mean, we know we're teaching it to get them past the exams. But actually, why are we teaching it for what this student does in 20 years' time? You know, do you as a teacher actually do this outside teaching it? Well, often the answer is no, not really. Whereas if you ask a teacher of English, for example, do you actually use the English you're teaching, at least some aspect of it, at least the language skills and things? The answer is yes, I use them every day. So I think one of the great things about the maths that I'm proposing, the computer-based maths, and computational thinking is they are skills that need to be used every day and can be used, and you can make progress in your life by using these skills more. And they also appear like they connect with people's lives right now, whether it's the students or the teachers. That in itself gives some confidence, because I think if you're trying to teach something very abstract and nobody's quite sure why you're doing it, it makes it actually quite hard to do. I think it's really challenging. So I think one of the ways to support teachers is to help them see the sort of confidence that can be built by having things that connect with real life very obviously. Another thing, and by the way, I think the pandemic, if there are, you know, from this ghastly pandemic, if there's something good that can come out of it, we're all used to being on Zoom as we are at the moment, or similar, and doing things remotely. I don't think teachers should be at all embarrassed about bringing specialists in to help in some classes and things. You know, you don't have to know everything as a teacher. As a CEO of a company, as I write in the book, I certainly don't know everything. I have many people who know much more than I do, who I work with. My job is to guide that, sometimes to jump into a problem, sometimes to zoom out. That's what our best teachers do, and I think we need them to do more of. That means sometimes you might run a class where you need some help. and you need some help on a topic to really guide the students, and that's great. And we have that opportunity now with all the technology. You don't physically have to bring them into the class. You can beam them in a Star Trek-like way. And I think that's a really helpful confidence booster as well as we get teachers up to speed. Just one final thing, which is I think we can get teachers sometimes from other subjects to help in this endeavor. So because when we're thinking about computational thinking and computer-based maths, we're typically starting from a context. The context is often, it might be from mathematics itself, or it might be from another subject. It might be, let's say, from science. We were talking about biology earlier. Well, if you have a biological context for the mathematics you're trying to teach, it may well be that some of our biology teachers can really help in teaching that, as well as our maths teachers.
Okay, that's really, I think we've got time for one more, Conrad, before we switch in and have a look at what's been thrown at you from today's session. And I think that the last area I'd really like to pick up on is about the link to other related subjects. So a group of questions asked about, yes, great proposed changes to the maths curriculum, particularly around computational thinking, but how do you leverage and synergize with the growing subject of computer science, which itself is perhaps also trying to put computational thinking at its heart? Yeah. Some overlap here, any conflict? How do we take advantage of that?
Well, there's no conflict, and there is definitely overlap. I mean, to put my cards on the table, I think if we look in the future, what we really want here is one computational thinking subject that mixes what we would currently call coding, the parts of maths we think are the right ones, and this sort of extra set of ingredients that I think makes up this modern computational thinking subject. And really, the fact that coding and mathematics are completely separate is kind of nuts, actually. Now, I'm very pleased that coding has started arriving back on the agenda. If you look at where is the sort of linkage between what I'm saying about computational thinking, computer-based maths, and coding, it's really in step 2 of this 4-step process that we talk about. So when you think about define, abstract, compute, and interpret, one of the big questions you have, so if you take a problem you want to solve and you define it, and then you abstract, we talked some time ago, we talked about very simple problem of, you've got 4 friends, I think it was, and you've got 12 sweets of candy and you want to divide it between them, right? So you're defining the problem as dividing, we're saying I want to divide it equally between them because I want to make it fair. So that's the definitional stage. We decided that fair equals equal in this case, which might always be the case. We're then abstracting. So traditionally what you do is you'd write down the division sum. 12 divided by, I can't remember if I had 4 friends or 3, but call it 4. 12 divided by 4. Now, that's a very simple case. We have a very simple mathematical notation right there. In fact, there are 2. There's sort of 12 with a divide sign by 4 and 12/4, for example. And by the way, the fact there are lots of notations is not terribly helpful to learning these things to start with. Now, at a more complex level, what are you really doing there? You're writing down a piece of code that represents, in a sense, the computation you want to go and do. And in the modern world, instead of writing lots of fancy squiggles and sort of hieroglyphics that you might have done, what you should be doing is writing computer code in some language. And that code, there are 2 reasons for this. Firstly, traditional mathematics does not handle many types of things you want to write down, like algorithms. It does a terrible job at writing down algorithms. You have to use all these weird signs like sort of therefore and implies and many other things. Code is set up for writing down algorithms as well as express. So you've got a much wider range of language effectively to use than in traditional maths. So that means you can more directly write down things that you want to say in a computational way. And the second thing, of course, is that we have these fantastic machines, computers, which can take that code and run it so that you don't have to do it by hand. So a key linkage between coding and computational thinking maths is this step 2, is how you write down the abstraction of what it is you're trying to solve. And in a sense, one of the issues I think with coding, as it's been reintroduced, it's not been quite clear in some cases whether you are doing the abstraction in the coding or whether you're just writing down abstraction you've already worked out. But whichever it is, we need to get people used to doing that abstraction and then to writing it down in a way that the computer can interpret. So in a sense, the coding is not just about making apps. Coding is about how you express yourself computationally in a world in which we need computational literacy across the population.
Thanks for that, Conrad. And just a quick word for those who asked questions in the 10th of June one and they weren't answered there by Conrad because he can't answer the 100 or so questions we've got in the first one. All questions will get an answer, just not on this session, I'm afraid. And now's the time, I think, to turn to some of the ones that have been coming in, some of which are intriguing, Conrad. So I'm going to put you on the spot with some of them. That's okay. And the first area, there's 2 or 3 questions asking one, which I know that is a big question and close to your heart. There's a question that says, what's the importance of math in our lives anyway, really? And a related question that says, would you share your perspective on why everyone needs to learn maths? And I know you've covered that in a variety of ways here, but maybe it's a chance to look at it broadly.
Let's hit those again, because they're really good and important questions. Look, I mean, you only have to listen to the coverage of what we do about COVID to know that maths is center stage in decision making right now. It might not be called maths, it might be called data science, it might be called, you know, modeling. But when we're talking about how literally life and death issues, right? I mean, it couldn't be more viscerally about life and death at the moment. A key issue is, you know, how do we protect ourselves? What do we do to, in a sense, minimize disruption? These are highly complex computational issues. And the only thing, I mean, you know, we can just hope and not, you know, just kind of just guess. Or we can try and work things out. Now, when you think about what's going on here, we've got a small elite who are basically telling us what the models are and why we should believe them. I'm not sure they're all right about them. I think some of them have overclaimed for what's possible to predict. I think that's caused difficulties. We've then got a mass population who really are almost totally unequipped to be able to query or understand much of what they're being told to believe. This is a bad situation. And as the world has got more computational, more mathematical over the last, you know, decades, this, you know, problem of the split between a small number of elite, in a sense, who are running away, you know, with a lot of power to determine decisions, and a large set of everyone else who are almost totally ill-equipped to understand what's been worked out to arrive at those, starts to cause this big sort of societal disconnect. And it's very interesting to look back at, you know, some of the things said before mass literacy. So I think one of the great successes of education over the last couple of 100 years is that in much of the world, people read and write. It's assumed, it's a right. You know, in most developed countries, there's a very, very high percentage of people who can read and write, who are literate. Certainly wasn't always that way. We used to have a small elite of sort of aristocrats and you know, high priests who pretty much wrote and told everybody what to think, and the rest of our populations had to go along with it and had a hard time questioning that. And that was, I think, a great improvement in our societies, is the fact that we now have this widespread literacy. By the way, another thing that happened, just to point out, is that a lot of people at the time before mass literacy said, oh, most people in the world are too stupid to learn to read and write. It's just something that only a few people can learn. Well, I think history has proved that completely incorrect. I think the same will be proven incorrect about computational literacy, which is what I've termed the mass use and understanding of computation. And I think in exactly the same way as literacy was important, so is computational literacy. Now, what's important is not learning how to do long division or quadratic equation solutions by hand. That's not going to get us to what we need to do. What's important is knowing things like what's a cause or correlation, can I understand this data? Do I believe what I'm being told in a reasoned way? Not let's throw out what any expert says. That's the wrong thing. Not let's believe what any expert says. Let's have a reasoned way of understanding and debating those topics by being able to question aspects of that. And I believe there's a great improvement we can make in that across the whole of society. We'll always have people who are these specialists, just like we have poets and we have writers, great writers, and so forth. We'll always have those people. That's not to knock that echelon, but we also have a set of people who use computation, who are literate in it, who use it every day, who make better decisions because they have that way of thinking about life. And that's kind of what we need. And that's the mathematics I believe we so badly need across our societies. By the way, one final point is I believe that will improve and increase the number of people who go into the higher echelons and become our top data scientists and others who use computation at a very high level.
Okay, thanks for that, Conrad. That's really good. There's while you've been doing that, the other thorny question of assessment has appeared in a few questions. And one of them says, where have we got to in using computers to fairly evaluate answers to messy questions?
Okay, that's an interesting sort of inverse of the issues that I've been talking about, and very important. Let me start from this angle. One of the problems with current assessments, I mean, there are many problems, but one of the problems is they've become more and more what I call closed-ended. A typical example is multiple choice questions. There are more assessments now done with multiple choice questions than used to be. And why has this happened? Because we need to make sure, because there's so much pressure to get the exact grade right and reproducible if you get 20 different people marking it, that you've got to have very right and wrong, yes and no answers to things. The trouble is the world is very nuanced. And actually, what we need people to understand is how to deal with a very nuanced world and come up with useful decisions. And so in a sense, assessments are going the opposite direction. They've become more locked down into yes or no answers. I mean, as a joke, that's something I often say is, how many times in your life have you had 5 answers to a question given, of which you know 4 are wrong and 1 is right? I mean, this happens all the time in assessments. It virtually never happens in my life. So one question is, how do we allow assessments to be quantitative, which I think we can't get away from? I wish we could get away from this sort of high quantitative way of looking at everything, or this very simplistic quantitative way of looking at it. But how can we do that while making them more open-ended? So I think there are ways to do it. I mean, old exams in English and history and things were more open-ended essay type things, and they managed to get assessments done on them, which people tended to agree were reasonably well balanced and you could reassess. So there are ways to do that. We can apply that to mathematics too. I think the question was about, can we get computers to go and mark those things, go and assess them? We're some way away from that. I think Wolfram Alpha is closer than most in being able to take a fairly, so to speak, messy, unsyntactic answer and hope to interpret a result from that. And actually, we have an early step of that if you look at our challenges website, which allows you to write bits of code and lots of different types of code, and for it to evaluate all sorts of things about that. That's still very close to the syntactic. So I think the answer is it's going to be some time before we have computers being able to really do a good shot at taking the kind of open-ended questions we want to be able to take in assessments. So we need to have humans involved for the moment. And if you have to choose between having humans involved, which costs a bit more, and having assessments that are assessing the wrong material, the wrong subject, you've got to pick the human route. Yeah. I'd love to see computers and our technology really push the bar on that, and we're doing that somewhat, but it's not there yet, and we shouldn't jump the gun.
Thanks, Conrad. We're good. There's a really rather interestingly different question here that says, look, we focused on the teacher and the school here, but actually there's an issue in the workplace and the home. We need computational thinking in most workplaces and in most homes. Given that children spend most of their time in a home, even before COVID, and even more so now, what can we do to support families and the workplace to move in this direction, as well as the education system?
Look, let me take the workplace first, because this is a very good observation. And one of the things we've been finding is that we built a bunch of computer-based maths modules, as we call them, for trying to manifest this vision. And I talk a lot about those in the book, and we have some samples of those up for people to try now on the web. And these are pretty early samples. They're not totally refined. They're what we could get up quickly. But I think they're very rich in actual content to use. The thing that's very notable about those, we built those mostly for, so to speak, secondary school. But actually, the topics there are as relevant all the way up to the workplace. They may not be pitched exactly as you pitch them to a 25-year-old instead of a 15-year-old, but the basic core issues in there are extremely relevant. So the plea I make is that anybody who's listening to this, who's involved in running an organization, who's involved in training in the workplace, please talk to us, because I think there's a real opportunity to have computational thinking training as part of the programs that are available already. You know, that many organizations, of course, have training programs. I think that, of course, there have been coding training has been available, has come to the fore in recent times. The thing with coding is it's great. It's a specific vocational skill so that you can go off and become a coder, or at least improve that, or do some coding. I think computational thinking is a little bit further back. It's a skill that all management needs in the modern world, many other people on the ground need, in order to make better decisions. I mean, if you have employees or people in your organization who need to make decisions, increasingly those decisions are based on data, for example, or models, or information that's being produced out of computing something. If you have no wherewithal for understanding how to be skeptical of those, how to poke at them, how to re-understand them, how to maybe even change a little piece of code, that puts you at a huge disadvantage in decision making. So please help us introduce computational thinking courses in the workplace. And if you go to computationalthinking.org, you will find some of the ways that we can help in particular, and you know, at all levels in that. I think at home, you know, the mechanism is slightly different, but the approach is similar. In a sense, we have some online training you can take. I think another thing to do is to start to discuss problems in a computational way. If you ever see anything in the news which cites data, really try to be skeptical. Use the define, abstract, compute, interpret style of thinking a little bit to start poking at it. When they say that COVID cases in my area have risen 22%, let's understand, you know, is it a percentage? Is it an absolute value? Were they very low in my area before? Were they high in my area before? How does this relate? You know, are we talking cases, or are we talking serious cases? Are we talking hospital? You know, start to poke at what this means and get used to doing that. And I think that's maybe a way to start in at thinking that way. And the more we can encourage that, the better.
Okay, thanks, Conrad. We've only got a few minutes left, so this may be the last one, dependent on your answer, Conrad. It asks the question, have you started to create a suggested map of the curriculum? And if so, for certain grades or several, how wide would it go and how wide does it go?
Yes is the answer. We have certainly tried to do that. We've started from, I would say, the sort of route is probably around early secondary that we've been thinking we put most effort in, because I think that's the area where we lose most people and there's immediate change to be made. We've done this in various ways. We started with an outcome tree. What are the outcomes we really want? And you'd be surprised, but around the world, when you look at those outcomes lists for mathematics, they are surprisingly sort of spurious in many ways. They jump from we need critical thinking. Well, that's very important, but what does it mean? To it's sort of very important that you know how to draw a bar chart and put ticks in the right place, which seems like it's sort of somewhere there down in the trenches. So I think getting outcomes that you're trying to affix to is a really important way to start to build out curriculum. Then you start to ask questions like, what exactly are the actual concepts and tools that you want to learn, and how do we structure these? We spent a long time trying to work this out. In my book, particularly in part 2 of the book, I go in some detail into our thinking so far and where we've got to in laying all of that out. There are many differences what we have at the moment. At the moment, the curriculum is very much a sort of, in a sense, a structure where you've got to follow a path in a very, very specific order. Clearly, there is ordering that's required in the computer-based maths curriculum we're talking about. But because we're dealing with concepts separated from tools and different levels of concepts, I think there are ways to have that not need to be quite as prescriptive as we've had in the past. You know, it's difficult because one of the problems is you've got to understand where is thinking. Where is it that we really, in the end, one way to look at where we go. So one question is, you know, if we look to the future in the AI age, as I call it, one of the big questions for education is, what is it that the human needs to learn, and what is it we can leave to the computer? And this is a really tricky problem, because it's a problem actually we've had throughout history when you get new machinery. It's like, do you need to learn how to build the machine? Do you need to learn exactly how it works to use it? And if it's a machine that a lot of people use, it's kind of mass machinery, you can't do that, because you don't want everybody to know how to build a tractor, to use a tractor in agriculture. Now we've got the same situation with computers, very widespread, almost ubiquitous, and driving a lot of what we do. We can't know how they work. So what is it we need to learn so we don't get caught out by them and we can make the most use of them? And in a sense, the big question for education going forward is that question. And computational thinking, maths, is absolutely at the center of that, because the subject has been so changed by the introduction of computers. So one of the chapters of my book is about what we call thinking outcomes. You know, what is it that defines the thinking? What are the pieces you need to understand? And it's very difficult. What do I need to know about machine learning? Well, there are many, many different levels of this. I need to know how to use it, where it's useful. That seems a fairly early staging. Where might I apply machine learning to my problems? What kinds of problems, right? Important. And by the way, something that typically isn't covered at all in our curricula at the moment. You know, where do I use quadratic equations? Where do those work better than using data science or using machine learning? That doesn't seem to appear in most curricula right today, which is a pity. That seems early stage. On the other hand, how do I build a new neural network to underlie machine learning? That seems a very late stage thing to learn. And so a lot of what we try to do is separate out. You can't just pick a topic and say this topic arrives at this point in the curriculum. You've got to say there are grades of this topic. And for the first time in our outcomes tree, I've not seen this anywhere else in the world, we have abstracted out different levels for each concept and tool that you might look at. And we started building, in a sense, a picture of what might occur early in primary, in secondary, and later, and to try and understand that. And that's sort of where we focused our energy. We've broken up the curriculum into about 5 categories, somewhat arbitrary, but useful to think, like data science, modeling, architecture of maths, information theory, and geometry. And you don't have to break it up that way, but it's quite useful. But I think those are much more useful ways to break it up than algebra, calculus, which are sort of quite unnatural divisions if you're thinking about this wider world. So that's a very intertwined answer for what's an extremely complex topic, much of which I try and cover in the book. And I'd love comments back on that if you manage to get to that. Incidentally, just a note on the book while I'm thinking about that. I mean, I've tried hard with the book to write something that I hope that many in the general public can read and absorb and understand, I've also tried hard to write a book that has a lot of detail and depth for policymakers, for example. Combining those two is not terribly easy. I wanted the depth because I want policymakers to understand we spent a decade figuring this stuff out, and I think we figured out quite a lot, and we have some pretty interesting things to say. On the other hand, I see this as a crucial movement for everyone. We talked about computational literacy earlier. It's important that everyone, parents, teachers, students, as well as governments and industry and everything else, are involved in the change needed, because it's a big change, and everyone needs to be involved. And so therefore it is important that everybody can get hold of some of the topics, and that's why I've tried to write the book in this way. So what you'll find in the book is, I think, it's in 3 parts. The first part is probably, I hope, pretty easy to understand in some ways. The second part, it has to get into quite some depth, and some people want to skip over some bits of that if they don't want all of that, all of those details. And the third part's, again, more into how do we deploy this, and thinking about some of the ways that change happens, not just in education, but in the world, and making comparisons between those. So I hope, again, that's going to be an area that's easy for everyone to understand. It may also be interesting for people involved in management and government, even if they're not specifically wanting to be involved in this change. So those are a few of the ways we've done this. And if we have a chance for some more time, we can maybe...
Well, I have to stop there, unfortunately, although there, perhaps as a segue into a final call to action, Conrad, that there are a set of questions in the things that come up today, which are really people asking for encouragement and motivation. There's there's a question from a student saying, what do you do if you're on a maths course and you're struggling and there's something better you should be doing, or you're a teacher and there's a better thing to do? Yeah. What do you do? So what's the call to action, Conrad?
So look, at several levels, I don't have a perfect answer for you, because the perfect answer is let's fix the whole system, right? And you can't do that, nor can I do that. Nobody can do that by themselves. So look, at one level, please, we've got a campaign that rolls out with the book. And I don't know, we can, we've put it up, the Take Action. So it's the campaign for computational curriculum change. I've left a word out because it's 5 C's. And what we want with that campaign, you see, one thing that's happened is that people who want to keep everything as it is have a somewhat united voice. Those who want to change have been, particularly in this space, in mathematics, very complicated what needs to change. We've discussed this over the last nearly hour, and it's highly complicated. It's been difficult, it's been rather fragmented, the reformers, because there are many different nuances of this, and correctly so, skepticism and different ways to think about this. So in this campaign, what we're trying to do is set out 5 principles that we hope many people who think this direction makes sense could agree to. So we've tried to lay out things that we think are the most, so to speak, as specific as we can be, but hopefully without, in a sense, alienating anyone on a matter of detail that isn't necessary at this point. And what we want to do with that is, the more people we can get involved in just saying, yep, I agree with these 5 points, the more we can take this campaign to policymakers and others and say, you know what, a lot of people want this change. This is a change you should look at. This is a vote winner. This isn't a vote loser. It's difficult to happen, but you've got public support coming towards you on this. Obviously, saying you agree with everything in my book. I'd love people to say they agree with every single word in my book, but that's not realistic. And maybe one day I won't even agree with every word in my book. We'll see. I do at the moment, I think, pretty much. But I hope you can agree with that. And so that as a sort of change for good, kind of change for computational good future, I think is a really important step that can be taken. But on the ground, personally, individually, what can you do? Zoom out from your predicament of having to pass some exam or having to teach to that exam, you got to do it. We have to do many things in life that we may not exactly like to do at that moment. Do the best you can on that. At the same time, set your head to, actually, there's a really exciting subject. It might not be exactly this one. Try to see if you can look at some of the problems we've put out and maybe other people in the space have put out. Try to get a grounding in the sort of direction I've tried to point people in with my book. And it was interesting, my TED talk about 10 years ago, surprisingly to me, one of the comments that came out when I gave that talk afterwards was, this is the first guy who's explained to me why maths has anything to do with my life and how it connects. So if you can even just get the idea from my book or other things, how mathematics connects to your life, I think that will really help you with the detail of what you might need to do in teaching or learning. I think that will, in particular as a teacher, I think that may give you more confidence to say, well, you know, here's where this plugs in, and that's why you might care about that, and that's what's interesting. Another way to also look at this, particularly as a teacher, is sometimes the big ideas that are not immediately practical, apparently, are pretty exciting. You know, what does randomness mean? How is randomness? Have I ever thought, most people know, sort of have an idea what randomness is, but it's kind of fun to think about that. So sometimes it's good to zoom out to those apparently bigger concepts. And I suppose the other thing is try to find some fun. Try to find some fun in it. Don't just get stuck in what can't be done, but try to look at what you can do. And you'll probably find there's more than you think.
Okay, thanks, Conrad. That's probably the point then to close on. I just need to say thank you to you and to everybody that's attended this session. Buy the book if you haven't bought it already. And thank you very much, everyone, for taking part.
Thanks to you all. Thanks for all the questions.
Cheers. Thank you.